Welcome, class, to Chapter 8 on sampling distributions. We're looking at the first two chapters here. Specifically, this is Section 8.1, I should say sections of Chapter 8. 8.1, the distribution of the sample mean. Here we're going to look at describing the distribution of the sample mean with a normal population and then do the same thing with a non-normal population. Statistics such as X bar, which is the sample mean, are random variables since their value varies from sample to sample. As such, they have probability distributions associated with each of them. In this chapter, we focus on the shape, center, and spread of statistics such as X bar, or the sample mean. The sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. The sampling distribution of the sample mean is the probability distribution of all possible values of the random variable X bar, which is the sample mean, computed from a sample of size n from a population with mean mu and standard deviation sigma. And so what we're talking about here is if you did multiple samples of size n, then you would have different X bars or means for each of those samples. And so that sampling distribution would be on your multiple tests, multiple tests of n observations, etc. The idea behind obtaining the sampling distribution of the sample mean is as follows. First, we obtain a simple random sample of size n. We compute the mean for that sample. And assuming that we are sampling from a finite population, we repeat steps 1 and 2 so that we collect multiple samples of size n, each with their own mean, until all distinct simple random samples of size n have been obtained, however many we choose to do. Note that once a particular sample is obtained, it cannot be obtained a second time. You can't go back and recreate the same sample or report it multiple times. That's, I think, is what it's talking about there, because then it would skew the data. If I kept reporting the same sample multiple times, that would skew the average or the sample mean of X bar. Our first objective is to describe the distribution of the sample mean for a normal population. An intelligence quotient, or IQ, is a measurement of intelligence derived from a standardized test. Scores on this test are approximately normal, with a mean score of 100 and a standard deviation of 15. The question here is, what is the sampling distribution of the sample mean for a size of n equals 9. If you look at this table from Minitab, this is a random sample of 9 scores, and you can see the scores from C1 through C9. And then in that last column, C10, this is the X bar, or the mean of that specific row. So rows 1 through 15 or 16, whatever's there, are just repeats of that experiment with a different sample, okay? And also notice that the person who is the second person in C2 is not allowed to be selected again, and that's part of the idea that you can't pick the same person for another sample, because then you're double counting them, etc. So we're sampling, you might say, without replacement. We're not putting those people back into the pool. Okay? So here we can see, and notice that the X bar is going to be different because we have 9 different individuals with 9 different IQ scores, and so the average for those 9 scores is going to be different per row in general. Figure A here on the left shows the distribution of the population, right? This is just all of the data for the IQ. These are all of the people that took the IQ test and all of the data reported, okay? In figure B, what we show here are the distribution of the sample means from column 10 in that last diagram from Minitab, okay? And so we can see that these are, the number of people that scored 100, the number that scored 90 or whatever, etc. on the IQ test. And so this is just our distribution of the sample means, of the means for each of the samples taken and then tallied all together. So if there were multiple samples with a score of 110, then that, is why that bar would be higher than another one. We can see from the shape here that it's relatively normal, right? The shape of the distribution is approximately normal. There's the curve. Here we have a normal curve, and we have the normal curve through here as well. The center of the distribution of the sample means is the same as the center of the distribution of the population. The center values are the same. But the spread of the distribution of the sample mean is smaller than the spread. You can see here it's a wider spread for the population than it is for the distribution of the sample mean. In fact, the mean of 1,000 samples is 100.02. The mean here is 100.02, whereas the mean of the population is 100. The standard deviation of the sample means is 5.01, which is much less, it's a third of the standard deviation of the population. So we draw some conclusions from this. The shape of the distribution of the sample mean is approximately normal. It's pretty close. The mean of the distribution of the sample mean roughly equals the mean of the population. And the standard deviation as far as spread is less than the standard deviation of the population. So let's look at an example. We're going to repeat the problem in the previous example with a sample size of n equals 25. Here we see a new histogram with n equals 25. This is the histogram of the sample means. Notice that the sample means appear to be approximately normal. It's still a roughly normal shape with the center at 100. The histogram in the figure shows less dispersion than the histogram in figure B, the one where we only had 9 samples, or n equals 9, I should say. This implies that the distribution of x bar, which is the sample mean, with n equals 25, has less variability than the distribution of x bar, or the mean, with n equals 9. Does that make good logical sense? Yeah, think about the, even though these aren't really large numbers, the larger the sample, we would likely expect that that would have less variation and be closer to the population as well. Okay? And there you can see the B diagram, and we can see that that there's less dispersion on the left with n equals 25 than on the right with n equals 9. In fact, the mean of 1,000 sample, the mean of the 1,000 sample means is 100.5, and the standard deviation is 3.08. Okay. Another thing to pay attention to is the size of the sample increases, the standard deviation of the distribution of the sample mean decreases. So as n gets larger, the standard deviation of the sample mean gets smaller. Okay, gets smaller because we have more data points. It kind of, to me, that makes some kind of logical sense, which statistics doesn't always, where it's a very rule-based system. And then understanding how to interpret those rules or concepts. Okay. So we're looking at the mean and standard deviation of the sampling distribution of x bar, right? The sample mean. Suppose that a simple random sample of size n is drawn from a population with mean mu and standard deviation sigma. These are the sampling distribution of x bar has mean mu, or the mean of x bar, is going to equal the mu, or the population mean. And interestingly, the standard deviation of the sampling distribution, the standard deviation of x bar, that's the x bar subtext there, is equal to the population standard deviation divided by the square root of n. And so we can see why that standard distribution is getting smaller as n is getting larger. The standard deviation, this standard deviation, sigma sub x bar, is called the standard error of the mean, how far we are away from the mean. The shape of the sampling distribution of x bar, if x is normal. If a random variable x is approximately normally distributed, the sampling distribution of the sample mean, x bar, is also approximately normally distributed. So if the variable, if our general population is normally distributed, then the sampling distribution of the sample mean will also be normally distributed, or that symmetrical. Okay. For example, let's look how this. The IQ scores are modeled by a normal random variable with population mean mu equals 100 and standard deviation of the population sigma equals 15. The sampling distribution of the sample mean, x bar, the mean IQ of a simple random sample of n equals 9 individuals, is approximately normal, with mean mu equals 100, and our standard deviation, so the means are going to be the same, and our standard deviation for the sample mean is going to equal the population standard over the square root of n, which is the square root of, okay? Describing the distribution of the sample mean. The IQ, reported as x, of humans is approximately normal, with mean mu equals 100 and standard deviation sigma equals 15. Compute the probability that a simple random sample of size n equals 10 results in a sample mean greater than 110. So what we're trying to do is figure out the probability that the sample mean, x bar, is greater than 110. The sample mean is normally distributed with mu sub x equals 100, and the standard deviation, sigma x bar, equals 15 over the square root of 10, which equals 4.743. The sample is a random sample, and the sample size is definitely less than 5% of the population size, that 9. The figure displays the normal curve with the area we want to compute, as you can see down here to the right. We're trying to figure out the area to the right of the score of 110, right? A sample mean greater than 110, okay? When we're doing probability, so remember the area to the right of that gives us the probability that the scores will be greater than 110. If we went to the area to the left, that would be the probability that the scores would be 110 or less than or equal to 110. Okay? Notice here in the diagram we already have the answer because this was created by a technical solution on probably Minitab. So to find the area by hand, what we have to do is convert x bar, the sample mean, which equals 100, to a z-score. Okay? So remember that here is the mean, the data point minus the mean over the standard deviation, okay? Well, when we're talking about a data collection that's actually data points that are all the x bar or the means of a sample, then we substitute those values in. So for x, we have x bar, we have minus mu sub x bar, And then remember that the standard deviation sub x bar is actually equal to the population standard deviation over the square root of n. So plugging in all those numbers, we get that the area, we get the z-score, which is 2.11. Now remember, when we get that z-score, we refer to table 5 to figure out what the area is to the left. And the area to the left is 0.9826 for a z-score of 2.11. That's that table on V that we looked at in the last section, or last chapter, okay? Since we want the area to the right, we have to subtract that table 5 entry from 1, because remember, the entire area under the curve is equal to 1, and the table 5 gives us the area to the left of that point. So that point and to the left, less than or equal to that point. So we subtract it from 1 and we get 0.0174, okay? What this means is that probability of obtaining a sample mean IQ greater than 110 from a population whose mean is 100 is approximately 0.02, right? 0.02, or 2%, okay? So the probability that the sample mean score will be greater than 110 is 0.0174. 0.0174, or rounded to 0.02. So what happens if we don't have a normal population curve? What happens then? Well, there's two key concepts. The mean of the sampling distribution of the sample mean is still going to be equal to the mean of the underlying population, and the standard deviation of the sampling distribution of the sample mean is still going to be equal to sigma over the square root of n. And this is regardless of the size of the sample. So no matter what the distribution is, these two concepts still hold. Now, what is interesting is that the shape of the distribution of the sample mean becomes approximately normal as the sample size n increases. So even though we have a non-normal population, as we take larger sizes of samples, those larger sizes of sample, the distribution of those larger sizes is going to become more of a normal curve, if you will, okay, regardless of the shape of the underlying population, whether the population is skewed left or skewed right. The sample mean, as we increase the size of n, is going to become normal, approximately. So let's look at an example. The data in Table 1 represents the probability distribution of the number of people living in a household in the USA. The figure below shows a graph of the probability distribution. So it's hard to see here. At least on my computer, I have a small screen, but this is the probability that there's one person in a household, the probability that there are 5, etc. And we can see that the highest probability is that there are 2 people, which coincides with the proportions over here. Okay. From the data in Table 1, we determine the mean and standard deviation number of people living in households in the United States to be mu equals 2.9 and sigma equals 1.48. Clearly, the distribution is not normal. In fact, the random variable is discrete, and you can see that here, right? Approximate the sampling distribution of the sample mean by obtaining, through simulation, 1,000 samples of size A, n equals 4, B, n equals 10, and C, n equals 30 from the population. The figure shows partial output from Minitab, where we're collecting samples of 4, and you can see that there. You can see the proportions there of each of the sample cases, okay? Column 1 and 2 represent the probability distribution for, this is just the sample number. And then each of the rows in 3 through 6, these are the actual the scores of 4 that we've noticed. And each row is a different sampling point, And then here is our X bar for that sample of 4 people. It's just the mean of those 4 inputs. Figure A shows the histogram of the 1,000 sample means for a sample of size n equals 4. We can see that the distribution is skewed slightly right, just like the parent population, but it's not as strongly skewed to the right. The mean of the 1,000 samples is 2.9 and the standard deviation is 0.76. So we expect the mean of the samples to equal the mean of the population, which it does, and that the standard deviation, notice when we do the calculation for the standard deviation, we actually get something that is close to the calculated value. Again, this is done by technology that you can see here on the right. Okay. Here we have figure B when we've increased the size of the sample or the size of n to 10 for each sample. The distribution of the sample means is also, again, it's still slightly skewed to the right, but it's not as strongly as B. So we can see already as we're increasing the size of n, we are getting a more normal curve. The mean of the 1,000 samples is still 2.9, and the standard deviation is 0.50. So again, the mean of the samples is equal to the population mean, and the standard deviation is once again close to the calculated value of the population mean over the square root of n, the number of samples that we're taking. Figure C shows the histogram, the last case, when n equals 30. So we've gone from a sample size of 4 to a sample size of 10, and now we're at a sample size of 30. The distribution of the sample means is approximately normal. Now we have almost a normal curve, which is what we supposed when we started this section or this objective. The distribution of the sample means is approximately normal. The mean of the 1,000 samples is equal to the population mean of 2.9, and the standard deviation here is 0.27. Again, the samples mean equals the population mean, and now because we have a normal model, the standard deviation of the samples equals the calculated value of 0.27, which equals that standard deviation. So we have something called the central limit theorem. Regardless of the shape of the underlying population, the sampling distribution of X bar becomes approximately normal as the sample size n increases. And this is what we observed again when we first started looking at this objective. So the question begs, how large does the sample need to be before we can say that the sampling distribution of X bar is approximately normal? The answer depends on the shape of the distribution of the underlying population. Distributions that are highly skewed will require a larger sample size for the distribution of X to become approximately normal of X bar, excuse me. So here we see a figure A in the top left shows a distribution of household incomes for a specific town. B, C, and D show the distribution of the sample mean for a random sample of households from n equals 4 to n equals 10 to n equals 25. Very similar to what we just did in the last exercise. Okay. Here we can see when n equals 25 that we get to really what looks like a normal shape or an approximately normal. And so if the distribution of the population is unknown or not normal, then the distribution of the sample mean is approximately normal, provided that the sample size is greater than or equal to 30. Now we got a normalized distribution with 25 only. And so this marker of 30, setting n equals 30, is really just kind of more of a conservative estimate. So if you're trying to make sure that you hit that conservative point, select the conservative normalized point, make sure you select n equals 30. Okay, let's look at one more example. Weight gain during pregnancy. The mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Weight gain during pregnancy is skewed right. An obstetrician obtains a random sample of 35 low-income patients and determines their mean weight gain during pregnancy was 36.2. Does this result suggest anything unusual? So the sample is a random sample. It seems reasonable that there are at least 700 low-income pregnant women in the population. That's kind of a farce, right? Of course there are. So the sample size is less than 5% of the population size. What's the sample size? Remember, they were picking 35 patients for a sample, and then we're assuming that there's at least 700 low-income pregnant women in the population, so 35 divided by 700 is less than 5%. So that's how that comes about. The probability is represented by the curve under the normal curve. The probability is represented by the area under the curve to the right of 36.2, like the other example we just saw. Okay. To find the probability of x bar is greater than or equal to 36.2, we have to convert the sample mean score of 36.2 to a z-score. And so we do that same thing, x bar, because we're using the means as data points, minus the population mean specifically related to x bar, which is actually the same, divided by the standard deviation of x bar. Okay, and I've done those calculations here. First we convert, the 36.2 is our value we're looking at for x bar, minus our population mean, which is 30, over our standard deviation of x bar, which is the population standard deviation 12.9, divided by the square root of n, which in this case is 35, which gives us 2.84. The area under the standard normal curve to the left of z equals 2.84 is 0.9987. Remember this value, once we have the z-score, we can go to table 5, and this gives us the area under the curve to the left of our value, 36.2. So again, since we want the value of greater than 36.2, which is to the right, not to the left, which is less than 36.2, we subtract this value, 0.0097, from 1. And we get the probability that's a randomly, the probability that we will select a person who's gained at least 36.2 or more pounds during pregnancy is going to be 0.0023. What we see here, there is no area there. I thought it was there. But if we plug that in and do a technology solution, we get 0.0022, which is very close to our estimate as well. So what is the interpretation of this? If the population from which the sample is drawn has a mean weight gain of 30 pounds, the probability that a random sample of 35 women has a sample mean weight gain of 36.2 pounds or more is approximately 0.002. That was what we calculated as the area under the curve to the right. This means about 2 samples in 1,000 will result in a sample mean of 36.2 pounds or higher. We can conclude one of two things based on this. Since the mean weight gain for low-income patients is 30 pounds, we just happen to randomly select women who are on average gained more weight. Well, I'm not so sure if that's possible when you say that we're selecting them randomly. The mean weight gain for low-income patients is more than 30 pounds. So the second one is kind of like, oh, we just got lucky. Oh, it's just a coincidence. And it's really kind of shirking some of the responsibility. The second one is actually developing sort of a hypothesis about what's going on, and specifically that low-income patients, the mean weight gain for a specific subset of the population, low-income patients, is likely more than 30 pounds. And so we're inclined to accept the second explanation over the first, mainly because our sample was obtained randomly. Therefore, the obstetrician should be concerned. Perhaps she should look at the diets and her lifestyles of her low-income patients while they are pregnant. Finally, this is just a summary. This is a table at the end of section 8.1. This is in your book. If the population is normal with mean mu and standard deviation, the shape, regardless of the sample size n, the shape of the distribution of the sample mean is approximately normal. So if the population is normal, the sample mean distribution is approximately normal. And again, we have this relationship between the mean of the sample mean will equal the mean of the population. And our spread, our standard deviation of the sample means, is going to equal the sample mean divided by the square root of n, which is the number of samples you're taking. If the population isn't normal, and we still have population mean mu and standard deviation sigma, as the sample size increases, the distribution of the sample mean becomes approximately normal. And remember, we set a bar there of saying that at n equals 30, you should have a normalized sample mean distribution. And here we have the same calculations as before. So really the difference here is when you have a non-normalized population distribution, the sample mean will become more normalized as you raise the value of n.